Welcome to the Explainer. So today, we're going to dig into something really fundamental about the world all around us. How the very same substance can exist in three totally different forms. From a solid rock, to a flowing river, to the invisible air we breathe.
I mean, really think about that for a second. You've got ice, which is a hard solid you can hold. Then there's water, a liquid that flows. And then steam, an invisible gas. It's all just water. So what's the big secret behind these transformations? Well, the answer lies deep, deep inside, right down at the level of its tiniest particles.
So to really get a handle on how things change, we first have to understand the states themselves. And it all comes down to two things: how tightly packed the tiny particles of a substance are, and just how much energy they have to move around.
Okay, so this table really lays it all out for us, the core differences. In a solid, see, the particles are locked into a grid. They're vibrating, sure, but they can't escape. In a liquid, those bonds loosen up, and that lets the particles slip and slide right past one another. And in a gas, well, they break free entirely. It's just a chaotic dance of particles filling up whatever space you give them.
So what this really means is that the state of matter isn't some fixed property. Nope, it's a direct consequence of energy. When we talk about heat, what we're really talking about is just giving these particles more energy, more freedom to move. All right, let's actually put this whole energy idea into action. We're going to follow a single piece of ice on its journey from a solid block all the way to invisible vapor just by turning up the heat. So picture this. We're in a lab with a beaker of ice and a thermometer. We apply a flame and the temperature starts climbing, -5, -2, -1. Then it hits 0 degrees Celsius and just stops. The flame is still on, we are still pumping in heat, but that thermometer does not budge until every last crystal of ice is gone.
Now, this is a fantastic little puzzle. I mean, we know energy can't just vanish into thin air, right? So if it's not increasing the kinetic energy of the particles, which is what temperature actually measures, then what in the world is it doing?
And the answer is this really cool concept called latent heat. The word latent literally means hidden, and that's exactly what it is. This is the energy that's being used up not to make the particles vibrate faster, but to actually break the rigid bonds that are holding the ice together. It's unlocking the particles so they can start sliding around as a liquid.
And this leads to a pretty wild fact when you think about it. Even at the exact same temperature, 0 degrees, the particles in liquid water have more total energy than the particles in ice. Why? Because they're carrying all that hidden energy that was needed just to change their state. Okay, so once all that ice is finally melted, the temperature of the water starts climbing again, 80, 90, 95, until it hits 100 degrees Celsius, the boiling point. And just like before, the temperature gets stuck. It will not go a single degree higher until all the water has turned into steam. This is where we meet our second type of hidden energy, the latent heat of vaporization. And it takes a huge amount of energy to do this, to give the liquid particles a muff of a kick to completely break away from each other and fly free as a gas. This is exactly why steam at 100 degrees can cause much more severe burns than boiling water at the same temperature. It's carrying all that extra hidden energy. But this solid liquid gas journey isn't the only road matter can take. Nature has some pretty cool shortcuts and other ways to influence these changes. And that shortcut? It's called sublimation. It's what happens when particles on a solid surface get just enough energy to launch themselves directly into the air as a gas. It's the reason why things like naphthalene balls in a closet or a solid air freshener seem to just slowly vanish over time without ever melting into a puddle.
And of course, the most famous example of this is dry ice. That spooky fog you see pouring off a block isn't smoke at all. It's sublimation in action. The solid is turning directly into carbon dioxide gas, which is exactly why they call it dry ice. There's no liquid mess.
Okay, so up until now, we've really been focused on temperature as the master control. But there's another major player here: pressure. While temperature gives particles the energy to fly apart, pressure does the complete opposite. By cranking up the pressure, we can physically squeeze gas particles so close together that their forces of attraction take over and they condense right back into a liquid. All right, let's bring all of this science right back home, into our everyday lives, with a process that's happening constantly all around us, even without a flame or a pressure chamber.
So let's talk about evaporation. See, unlike boiling, which happens throughout the entire liquid at one specific temperature, evaporation is really a surface game.
At any given moment, some particles right on the surface of a liquid have just enough kinetic energy to break free and escape as a vapor. It's a slow, quiet kind of transformation.
And the cool thing is, we use these ideas all the time, probably without even thinking about it. Your laundry dries faster when you spread it out. That's increasing the surface area. It also dries way faster on a warm, windy day, but much slower when it's humid, because the air is already kind of full of water. Which brings us to probably the most personal application of this entire explainer. We all know that sweating cools us down, but how does it actually work? What's the physics behind it?
It all circles back to that hidden energy we talked about. For your sweat to evaporate, it needs to absorb the latent heat of vaporization. And where does it get that energy? It pulls heat directly from your skin. So as the sweat escapes into the air, it literally leaves your body's surface cooler. It's your own personal air conditioning system.
And this simple bit of science is exactly why what you wear matters so much. Cotton is great in the summer because, just like the quote says, it absorbs sweat and spreads it out. That creates a larger surface area for evaporation to happen, cooling you down faster. So after this whole journey, from ice to water to steam, through the shortcuts and right into our own bodies, it really all boils down to these two fundamental forces. Temperature and pressure are like the puppet masters, dictating the state of almost all the matter around us. The thing is, once you know what to look for, you start seeing it absolutely everywhere. The dew on the grass in the morning, that ring of condensation on a cold glass, the steam rising from a hot cup of tea. It's all just matter, dancing between states. Thanks for watching.